everyone, thanks for joining this presentation. I'm Claudia Misale. I'm a staff research scientist in the hybrid cloud infrastructure team at the IBM TJ Watson Research Center. I'm excited to share the stage with Vanessa Sochat. She's a computer scientist at the Lawrence Livermore National Laboratory in California. In this presentation, we will talk about Cloud and HPC Convergence, targeting job management on Kubernetes clusters through the Flux Job Manager. Cloud is a dominant market for computing, and it's influencing HPC as well. But why is cloud so appealing? It facilitates portability and reproducibility, for instance, through containerization. It enhances resiliency and efficiency, for instance, through resource dynamism and elasticity. And it reduces also complexity through automation, for instance, with autoscaling, elasticity, and declarative management. So let's start with some numbers to give a little bit more context to cloud and HPC convergence. So public cloud revenue was forecast by Gartner to be around $500 billion in 2022, reaching about $600 billion by the end of 2023. We can contrast that spending with HPC spending in cloud, which was forecasted to be about $32 billion in 2022. There is not only a very large interest, but the interest itself grew very rapidly in the past few years. There is a lot of interest to incorporate HPC in cloud, not only from a technology perspective, but also from a usability perspective. In fact, many users and developers from financial, automotive, or telco institutions want the benefits of cloud with the enhancement provided by HPC. The trend of integrating technologies from each community leads to converged computing. Converged computing, or an environment that seamlessly combines the performance of HPC with the portability, reproducibility, and automation of the cloud, is an active area of research and development that seeks the benefits of both worlds. When we talk about cloud in this presentation, we will refer to Kubernetes, which is the de facto container orchestrator framework. The flagship conference for Kubernetes is called KubeCon and Cloud Native Conference, and this is a very large conference which reached almost 17,000 registered attendees for both virtual and in-person attendance. More than 7,000 people attended last year's North American edition. From the research side, there is interest in bringing the advantages of containers and cloud in HPC, and several workshops are addressing topics related to cloud and HPC convergence. An example is the Canopy workshop at Supercomputing Conference, or a Birds of a Feather about converged HPC and cloud computing, again at Supercomputing in 2022, and the Kubernetes Batch and HPC Day at KubeCon 2. There is an increasing interest in moving state-of-the-art composite workflow to the cloud, or use the cloud for bursting purposes. But it can be very challenging for those workflows to take advantage of the cloud. Many current cloud technologies cannot satisfy scientific software demands for performance, and cloud computing can definitely benefit from the experience and research into performance optimization that the HPC community has worked on for decades. For instance, the MAMI workflow, the multi-scale machine learning modeling infrastructure workflow, it couples a macroscale model for spanning micrometer length and millisecond timescale with a microscale model employing high-fidelity molecular dynamics simulation to model RAS protein interaction with cell membrane. RAS protein mutations are involved in a large number of cancers, and it has been used up to 4,000 nodes of the Sierra supercomputer, currently utilizing over 16,000 GPUs and 117,000 CPU cores, and running up to 36,000 different tasks. The MUMI workflow requires high throughput scheduling capabilities, and this requires having high-performance resource manager that could efficiently schedule such tasks over converged environment. This is an architectural diagram of the American Heart Association molecular screening workflow, which combines MPI simulation analysis with machine learning and containerized components as well. This is a cross-cluster workflow, and it has components running on CPU cluster, some components running on GPU cluster, and another component runs in a Kubernetes cluster, providing a queue that connects those two main components. We are seeing pattern at the US national labs and beyond, and there are other examples such as traditional HPC simulation coupled with AI and machine learning surrogate model, as well as potentially orchestrated databases. Despite being examples already at the labs, we anticipate that there will be more in the future. And a survey, in fact, said that around 73% of the workloads running at the Lawrence Livermore National Laboratory are interested in cloud integration. Unfortunately, most traditional resource managers and schedulers are not suited to address the challenges of converged computing. Among the disadvantages in the HPC area, we see that scheduler and job manager, they cannot orchestrate container lifecycle and networking. That is something that Kubernetes platform can do very well. And they're not designed for elasticity. On the other hand, Kubernetes also shows some disadvantages for converged computing. For instance, it's only designed for loosely coupled application. The Kubernetes scheduler is very limited, and also there are limited resource expression for HPC. For instance, some mitigation are being taken through the not feature discovery, queuing mechanism, or the GPU operator, but still there is a lot of work to be done. To further the convergence, we really need to improve the interaction between those two components. As an example, let's say we want to port a traditional MPI workload on Kubernetes. So we need to create declaratively a Cloud and HPC slice, and this requires a couple things. We need to scale the MPI bootstrapping on Kubernetes and also find high quality pod placement. The idea is that you have a larger complexity when mapping the MPI workloads on Kubernetes rather than just on bare metal cluster. And you have also to map MPI ranks to pod and then map those pods into the underlying physical infrastructure. In our experiments, we run the MPI workloads on Kubernetes by means of the kubeflow MPI operator. The first thing we had to address was to allow the MPI operator to scale 3 times order of magnitude higher than what it was providing. So going from around 80 ranks up to 16,000 MPI ranks with an Hello World program. We fixed a set of limitation and race conditions to allow that, and we hope to get those changes merged very soon in the upstream MPI operator. The second component is Fluence, which brings HPC scheduling in Kubernetes, but we will touch on that later in the presentation. Now I will let Vanessa take over and talk about Flux.
Gracias, Claudia. Hola, soy Vanessa. Soy una científica de la computación en el Laboratorio Nacional Lawrence Livermore y estoy muy emocionada para estar aquí para hablar sobre el proyecto Flux y Operador. Hi, I'm Vanessa. I'm a computer scientist at Lawrence Livermore National Lab, and I'm super excited to be here today to talk about the Flux Framework project and the operator. We develop a project at the lab called Flux Framework. It is a job scheduler that combines hierarchical management with graph-based scheduling. And the reason that it's called a framework is because it's actually a group of sub-projects that when you put them together, they manifest in the scheduler known as Flux. So you probably are asking, what is hierarchical management with graph-based scheduling? Let's say that we have a resource allocation of 4 nodes. These could be on a high-performance computing system. They could be on the cloud. It really doesn't matter. If we install Flux and we start what's called a Flux instance, that instance can see the 4 nodes that are available to it as resources. Now, when you launch a job, that Flux instance is going to create actually instances of itself. So Flux instances running on each of the sub-resources, each of which can see the specific resources on, for example, the node. And so what you're actually looking at here are different levels of a graph where each can actually see and validate its own resources. You could also look at this as a more traditional graph. So on the right here we see the top level node is the cluster. Of course, the subcomponent of the cluster is you have racks. Here we only have 1 rack. In real life, you probably have many racks. And of course, each rack has 1 or more nodes. And the reason that we have pink and marigold here is because we're not just modeling the physical things, so the containment subsystem, we're also modeling the network subsystem. And this is a really powerful approach because it means that Flux is flexible to change as technology changes. So we know for a fact that in the future, systems are going to change technologies. And for Flux, it will just be a matter of adding new kinds of resources to this graph. It's also really powerful because when you submit a job, Flux will be able to look at the requirements of your job and look at the resources available and best match those 2 things. So Flux is really flexible, and that means that it can schedule resources nearly anywhere. So here you see a listing. There are sort of the obvious contenders. So bare metal, virtual machines, doesn't matter if they're in the cloud or not. Of course, high performance computing systems, that's where it all started, right, folks? But some of the kind of more niche and unexpected use cases are, for example, nested in another workflow manager. So this is actually what we suggest people to do if they don't have an entire supercomputer running Flux. You can, for example, start a Flux instance within an SBatch command for Slurm, and conceptually you have your own entire mini supercomputer within that SBatch job. That is super cool. And you could also create a Flux cluster, for example, running across pods in Kubernetes, which is something I'm going to be talking about a little bit later. Another really cool part of Flux is that its internals are really rich for communication. So aside from sort of the facilitated communication between Flux instances, Flux also has messaging overlays and data stores that are directly built in that mean that jobs and tasks can connect directly to one another. And so as a very kind of simple and direct example of this, I want to show you some experiments that we did at the lab. So what we're looking at here is schedule throughput, so jobs per second, as a function of the number of cores. And so for these experiments, we ran 3 levels of schedulers. So on the first one, the red scheduler, this is sort of a traditional workflow manager where it's not going to really adjust its rate or strategy based on the number of cores. Now, for the second level, the blue line, we're actually going to have 2 levels of Flux instances, where the second level of instance is actually going to be controlling 32 cores. When we do that, the submission rate has a 45 times increase, which is huge. So now what happens, of course, if we add another level, so the green line, when we add a third level, and then that third level Flux instance is only controlling 1 core, we have a 60 times increase over that original red. So that is like super impressive. And this is a simple case because it's just submitting jobs, but you can imagine how this applies also to the tasks in your workflow. If you are a developer, you may like to know that Flux has really rich, well-defined interfaces. This is one of the most exciting things for me when I joined the Flux project last year. So aside from, the traditional client that you'd expect from most job managers, we have Python, we have Go, Rust, C++. If you are a developer, you are empowered to build things that use and sort of are around Flux. We also, as of last year, have a RESTful API that is available. So all together now, if I had to choose one term to describe Flux, that term is flexibility. And we believe that this flexibility is really key for working in this converged computing space. So if you want to know all the things about Flux, we have a place for you. You can go to fluxframework.readthedocs.io. We have quick starts and tutorials. We have comparison tables. We have detailed guides for different use cases, like if you're an administrator or other things as well. Okay, so now let's kind of go back to this original converged computing space. If you think of it very practically, it's like this continuum between cloud and HPC and cloud back again. It's bi-directional. And one of the challenges is really understanding the challenges, the weaknesses, the trade-offs, the differences, the different components that you kind of have to compromise as you move between these spaces. And so in our converged computing work, what we're trying to do is figure out the right convergence of technologies for a specific use case and optimize that. And there's sort of 2 sub-questions to this. The first is very obvious. It's like, okay, can we create integrations that combine the best of both worlds, create something that is greater than the sum of its parts? But the second question is a little more subtle, and I actually think it's incredibly important, so I want to bring it up. And that is, can we open up opportunities for collaboration between traditionally very disparate communities? Because it's truly understanding the trade-offs, the strengths, the weaknesses as we move along this continuum that is going to directly impact how we make decisions for future systems and workflows. So let that sink in. The learning that we do today is going to directly impact our systems of tomorrow. All right, so if I can read your mind again, you're probably looking at this line and you're like, hold on, Vanessa, this is a continuous line. Continuous lines have an infinite number of points, which means potentially infinite number of projects. I just don't have time for that today. And I also do not have time to present an infinite number of projects, so don't worry. We are going to be talking about 4 very specific projects that we've started that are working in this converged computing space. If you've been paying attention, you probably could guess that most of these projects are going to involve Flux framework. We really see Flux as this vehicle that's going to allow us to flexibly move between these 2 spaces. And so the other component that is super important is Kubernetes. Kubernetes has become the de facto, the leading container orchestration framework in the cloud. So we are going to put these 2 together in a nice little heart there. And we're going to be looking at integration between Flux and Kubernetes 4 different ways. The first way is going to look at the Flux scheduler with Kubernetes. This is a project called Fluence that Claudia is going to present. And conceptually, this is like, I want to make a pod in Kubernetes or some other standard Kubernetes object, but I want Flux to do it. The next project is flipping that around a bit, Flux running inside of Kubernetes, so having your own Flux cluster inside of it. This is a project called the Flux Operator that I'm going to be presenting. The third project is looking at Flux as an external orchestrator, so flipping everything again. And this is something I alluded to a little bit earlier, that basically Flux can understand other things as resources in its graph. So we want Flux to understand Kubernetes as just another resource in its graph. And then finally, we're interested in elasticity. So we want to dynamically scale up and down based on the needs of a workflow. On that note, I'm going to pass it off to my colleague, Claudia, who's going to introduce you to Fluence.
In this part of the presentation, I will discuss what are the requirements to run HPC workloads on Kubernetes, and I also will talk about the Fluence plugin scheduler for Kubernetes that is built on top of Flux Scheduler. To run HPC or AI workloads, we need to fulfill the following requirements that are missing in the default Kubernetes scheduler. So we need to have batch scheduling and schedule the application as a single entity, be able to express hardware topology and use that to do a better placement. Also allow application to use resources exclusively or not, and also choose among different placement algorithms that better suit the application requirements. With batch or group scheduling, we mean that the application composed of different replicas needs to be scheduled as a single entity, because the application will not work if any of the replicas stays pending. To solve this, we can use the podgroup CRD and the co-scheduling scheduler plugin from the upstream Kubernetes that are published in the official scheduler plugin repositories. Fluence reuses the podgroup custom resource definition to label pods and gather them to build a single batch. Then it creates a request to Flux to schedule it and in an all-or-nothing fashion. And since Fluxion is a batch scheduler, this was very easy to enable. For instance, if we want to schedule an MPI job with 4 replicas, we get an allocation if and only if there is enough capacity to start all of the 4 replicas. Fluence resource model is graph-based, and the topology is at cluster level. When Fluence starts, it builds a graphical representation of the Kubernetes cluster and uses it as an input to Fluxion. Nodes in the graph can represent availability zone if this information is available, then nodes, memory, CPU, GPUs, but also other software information if enabled by the node feature discovery operator. Multi-tenancy is a core component in Kubernetes, but HPC applications are not friendly to noisy neighbors and would rather run undisturbed. With this representation, it is easy for Fluence to allocate workloads to a specific availability zone, for instance, to optimize latency or just assigning exclusive resources to application, starting from any level of the topology. Let's consider an example where we run 2 molecular dynamic simulation and other services. Each molecular dynamic simulation benefits from not sharing resources with the other one. and each simulation needs their MPI ranks to be closer to lower latency. Fluence will use the pack policy to place the MD simulation on a subset of the cluster and place the services on the remaining nodes. Lastly, upstream Kubernetes provides different placement algorithms via profile, and the scheduler framework makes it very easy to create custom scheduler plugins. And we take advantage of the scheduler framework to implement our HPC-grade scheduler plugin Fluence. Fluence already implements different flavors of pack and spread, which are useful to schedule workloads with very different requirements, for instance, if they're network intensive or compute intensive. Also, high-level or low-level constraint can be specified at the job level, which can also produce different placement results and make it very flexible. The Fluence plugin scheduler for Kubernetes is implemented on top of the scheduler framework to promote portability and easy integration with Kubernetes. The scheduler framework allows the extension of the default Kubernetes scheduler with some custom logic, which means that by using the framework, we're basically implementing on top of the default scheduler. The green label in the figure on the left are called the extension point, and those can be customized with the preferred logic. Since the scheduler framework is used to extend the default scheduler, it exposes the same functions the default scheduler implements. In Fluence, we implement the pre-filter and filter extension points, avoiding completely the scoring part. And we let Kubernetes do the node reservation, pod allocation, and its execution. Fluence uses the Fluxion scheduler module as a library, which is made accessible through a Golang binding. And we run this component as a sidecar container, and Fluxion runs as a service to the main container, which implements the extension points. The Kubernetes default scheduler is always running in the cluster anyways, and even more scheduler can be added, and they will all compete for the same resources. Fluence, we've seen that it has its own internal graph-based representation of the cluster resources, and they are managed in the sidecar container. And it keeps track of the existing allocation made by Fluence. While the default scheduler is aware of the resources being used by the pods scheduled by Fluence, the vice versa is not true. For this reason, and also to avoid noisy neighbors, it is recommended to use Fluence on a dedicated set of nodes. So let's see quickly the execution flow. At startup, Fluence gets information about the nodes in the cluster and builds the cluster topology to start the Flux scheduler library with. At this point, Fluence is ready to get the pod's allocation request. When we get an allocation request, the plugin converts the pod manifest into a specification format that Flux can understand. A match allocate gRPC call is submitted to the sidecar container, and if the allocation is possible, the result is given back to the Fluence plugin, which will inform the Kubernetes infrastructure that the pod can be now executed on that particular node. We evaluated the allocation at runtime of a simulated workflow consisting of Core2 benchmark used to evaluate exascale system by the Department of Energy and the National Nuclear Security Administration in the United States. These are either latency sensitive or compute intensive workloads, and they are implemented on top of MPI. We evaluated those on an OpenShift cluster on IBM Cloud and a Kubernetes cluster on AWS, and we used the Kubeflow MPI operator, which we modified to allow to scale up to thousands of MPI ranks, as we mentioned earlier in the presentation. The evaluation is done Fluence versus the default scheduler, which we configured to make it allocate as close as possible to what Fluence could do. We will not go into the details, but we will show the main takeaways. The main message of this slide is about what we cannot do with the Kubernetes scheduler. I want to emphasize that QMC pack and LAMPS pods need to be packed on a single node first before moving to the next one, because they need to communicate and they are network intensive. So on the left side, we show some results on the IBM Cloud OpenShift cluster when running both with Fluence and the Kubernetes scheduler. We managed to get LAMPs to run at least to completion on 3 availability zones, but with the Kubernetes scheduler, the performance are very poor because of the spreading. Even when using just 2 availability zones instead of 3, so forcing it to pack on 2 availability zones first, it wouldn't make much difference in terms of performance. With QMC pack, the Kubernetes scheduler cannot make it run to completion of 3 availability zones because it crashes thanks to the spreading placement. So we have to limit the Kubernetes scheduler to place the pods on 2 availability zones with affinity. Fluence would anyway put 2 on 2 availability zones because it's using the packing placement. So we don't need to do anything other than choosing the right placement algorithm. Despite the affinity, we can notice that the execution times are higher, and in the larger scale, the variability is quite high. On the right side, we show the evaluation of AMG and QMC pack on AWS EKS. This example is quite interesting because we are using the entire cluster for each workload, and it emphasizes how the random type breaking used by the default scheduler, where nodes get the same selection score, will impact significantly the execution time of the applications, resulting in an extremely high variability. On the other hand, Fluence placement algorithms allow consistent placement of pods, resulting in very low variability and consistent performance for the application. The kube scheduler was unable to pack on single node first, so even when limiting with affinity, the Kubernetes scheduler would spread across the nodes. In summary, we can say that the workloads scheduled with the Kubernetes scheduler can be up to 3.5 times slower than the one scheduled with Fluence. And we can also see a higher variability with the kube scheduler, especially at the larger scale. Also, the Kubernetes scheduler is not very easy to pack on single node first, and even with limiting with affinity, the Kubernetes scheduler would still spread on multiple availability zones, for instance, in our example. So for the last part of the talk, Vanessa will take us through a very exciting project, the Flux Operator, and then she will conclude the presentation.
For the second project in our converged computing space, we are going to be talking about the Flux Operator. This is Flux running inside of Kubernetes. Now, some of you probably are not familiar with what an operator is. In very simple terms, an operator is a controller for a Kubernetes cluster to manage objects. And this term actually goes back to kind of what you would think, referring to a human operator. So it used to be back in kind of the early days of Kubernetes, if you imagine that you were managing a cluster and you had to do something, for example, to increase the size of a database, you would have to manually be that operator, manually apply YAML files and, create new pods, all these things. And so someone in 2016 was like, we should probably automate this because this is a lot of work. And so they came up with this abstraction called an operator. And so how does an operator work? Well, it starts with you, the Kubernetes user or admin, and you're very happy because you have not been burned by Kubernetes yet. And then there's this thing called a custom resource. So a custom resource, you can think of it, it's very conceptually similar to like a pod or a daemon set, a Kubernetes API object, except it's created by a third party, such as you, such as me, to create kind of a custom application within Kubernetes. So you, as the user, how are you going to create these custom resources? Well, if you had to guess, it is YAML. So you apply a YAML file to the cluster. This is called a custom resource definition because it's defining the custom resource. And then you're going to be able to create things such as mini clusters. So our custom resource for the Flux operator is called a mini cluster because it's kind of like a mini cluster in Kubernetes, that kind of thing. And if you've ever seen these YAML files before, the custom resource name actually maps to the kind. So here you can see that it's a kind mini cluster. So what's actually happening? Well, the operator is going to be watching for events from the mini cluster custom resource. And then when it gets an event, it's going to look and say, okay, I have this new request. This mini cluster needs to look like this. Let me look at the actual cluster and compare those two. Do they match? And if they don't match, well, the operator is basically going to keep adjusting the state until they match. And this is incredibly simple, but this is literally what an operator does. It's basically like a reconciler or a loop that keeps doing that until it gets to this desired state. So the Flux operator, when we put these things together, is a controller that allows us to set up a Flux instance to run across pods in a Kubernetes cluster. And we call this set of duplicate pods a mini cluster, as I alluded to earlier. And if you're familiar with Kubernetes abstractions, we are using an index job, which creates a duplicate set of pods that's going to create this instance. And this is part of the batch working group jobs API, and I believe was new sometime last year. So conceptually, let's say that we have a Kubernetes cluster of size 9. We can also create a mini cluster of size 9 to maximally utilize our resources. That's what it looks like. Now, how would this actually work? Is it just a bunch of like pods? Are they talking? Like, what's going on? Well, we have index 0 of this index job is called the broker. The broker is basically in charge of orchestrating the jobs. That is going to happen via communication via a tree-based overlay network. So if you're familiar with Kubernetes, what we're going to do is create a headless service. So all of the pods can see each other from a networking point of view. They all have fully qualified domain names. So then once, the broker starts, brings up this cluster, you have all the niceties of a traditional cluster, batch jobs queuing. The Flux running in these pods doesn't know that it's not running on bare metal. And then submit away, Meryl. Your cluster is up, you're done. Okay, so I noticed from these talks in previous years, they're very applied. And so I wanted to present to you front and center, very strong use cases for the Flux operator. So the most basic use case is to create one mini cluster per job. And yes, this is like bringing up all of these pods, running one thing and bringing them down. Is that incredibly inefficient? Absolutely. But it actually is very good for understanding the effectiveness of this. So what would that look like? Well, you as the user, the super cool Gopher guy, that is you, you're going to define your job parameters. So the container, the image, the size, in the YAML file, the custom resource definition. You're then going to apply it and you're going to give it to the Flux operator. The mini cluster will be created. You might save output or logs as you go. You want to know like what your lamps run results are. The job is going to complete and clean up. And yay, you're done. Congratulations, you just did the whole up and down kind of symphony kind of deal. Now, the reason that we have this design, or the reason that it might actually be important to kind of look at the up and the run and the down, is because we can get a better understanding of how efficient these steps are. So what you're looking at here are mini cluster creation and deletion times. We're moving from a cluster of size 8 up to 64. These are experiments that we ran earlier in the year. And what you see is that with the index job, this scales really nicely. We're not seeing like crazy exponential growth here. Okay, so let's step back. The more realistic use case is that you want to bring up a persistent mini cluster. So bring up the cluster, submit jobs to it until you're done, and then bring it down. And so there's several ways to do this with the Flux operator. If you're super like old school and you definitely want to have a command line, you can have your command line. So you can literally shell into, for example, the broker pod and Flux submit directly. And it's just like you have your own HPC system. We also have Go and Python SDKs for the operator. So you can, for example, write logic into a workflow tool that can orchestrate bringing mini clusters up and down that may be matched to workflow. And actually, I have a pull request into SnakeMake that does exactly this. As I alluded to a little bit earlier, we also have a complete RESTful API. And this is really nice if you want sort of a more controlled set of endpoints. So for example, you can see here, there's the expected interactions to submit a job, get information about jobs. This also has an OAuth2-like style flow. So you can actually create multiple users and then basically have them make requests to the API. There's authentication, there's a shared secret, so the payloads are encoded. And if you absolutely hate command lines, actually the Flux RESTful API comes with a web interface where you can submit jobs and you can look at them in a table, or you can look at the output. So here we're looking at my Pokemon's Python module, and we're looking at the Flapple Pokemon. So I want to point out also that the Flux RESTful API is like not specific to the operator. You can bring it up with Flux in a single container on an HPC cluster. It's generic, but I will mention it with the operator because if you create a custom resource definition without a command, it will automatically install this application and start the RESTful API for you, anticipating that this is what you want. So the final kind of interaction for the Flux operator with this persistent cluster is actually a tool that we made called Flux Cloud. We made this explicitly to run experiments earlier in the year. So Flux Cloud makes it really easy to basically define your experiments in a single YAML file. And then as you see here, there are 3 commands. So Flux Cloud up will bring up your cluster. Flux Cloud apply will like run all your experiments and you can just kind of watch. And then Flux Cloud down will bring everything down. Okay, so we are in the process of trying to take a lot of use cases, workflows that we have at our different institutions and map them into Kubernetes, map them into the Flux operator. So we're creating a bunch of tutorials and examples of doing all of the things that you see in the list here. So simulations, machine learning, saving state, services, singularity containers, multi-tenancy, and many different kinds of storage, like, oh my! So if you're interested in any of these things, the best place to go is the Flux operator documentation, linked at the bottom here to see our set of tutorials. Okay, so to step back a bit, when we first came up with this project to kind of do due diligence, we really needed to compare it to kind of the best in the space, which at the time was the MPI operator. So if you haven't heard of the MPI operator, it started as part of the Kubeflow project. It is another operator, but it defines an MPI job as its custom resource. It has a little bit of a different design, so it uses a launcher node to coordinate workers via SSH. It is similar in design because it also uses a dedicated host name and a service for the workers. And I will note that we had to use a slightly modified version to scale to over 100 MPI ranks. If you're interested in that work, please see the reference at the bottom of the slide. So for our experiments, we wanted to run LAMPs. Probably everyone here is familiar with LAMPs. I don't need to say much about it. And for the design, we wanted to bring up one size 65 node cluster. So even though we're running experiments on size 64, we need that extra node because the MPI operator needs that launcher node. So we want to be creating mini clusters or a set of pods for each of sizes 64, 32, 16, and 8. And it is super important that these are running on the same Kubernetes cluster, because if you're bringing up different Kubernetes cluster, you might as well be comparing apples and oranges. So for our experiments, we created this really big cluster. Well, I guess it's not that big, but for cost-wise, it's really big. And then for each of the MPI operator and Flux operator, we either launched a job or we created a mini cluster across those sizes. We ran LAMPs 20 times, we recorded the timings, and we saved the output log. And this was being done with Flux Cloud, so mostly we were just monitoring that. And then we get to look at the results. So how do the setup times compare? I want to step back and note that because of the design that they're so different, we can't compare these side by side. So we're going to compare them separately, starting with the MPI operator. So you're looking at MPI operator end-to-end time. This is when you're looking in the logs of the launcher node, and it's from the notification of the job received through when it's completed. I want to note that it is very important that in this frame of time, the pods are ready to go. There's no waiting for pods. This does not include the LAMPs run. And what you see very directly here is that time increases twofold between the cluster sizes of 8 and 64. Now, the closest thing we can compare for the Flux operator is a Flux start end-to-end time. So this is when the broker comes up, does have to wait for the other worker pods because we don't know when the other pods are going to come up relative to the broker. It also does not include the LAMPs run. And you kind of look at this and you're like, huh, this scales pretty nicely. Double thumbs up. So for the actual things that we can compare side by side, we finally have 2 colors on this plot. We looked at Flux submit versus MPI run. So you're probably familiar with MPI run. You would do MPI run, some set of options, and then the LAMPs command. We would sub in Flux submit to that because Flux, has the MPI library sort of built with it. And so we can compare these things side by side. And obviously this does include the LAMPs run sort of being wrapped in this command. And what you notice is that for these experiments, the Flux operator is consistently faster. And we think this is probably related to the 0MQ bootstrap. And this was just a fantastic result because when we ran this, the project had been around like 4 months, and the MPI operator has been around for maybe 4 years. So when we compare the LAMMPS runtime, so basically looking at those timestamps within the LAMMPS logs, they do get smaller, so much closer in time. But we will point out that, like, although this is like a small LAMMPS run, if you were to scale this to a larger set of jobs, this could really translate to cost savings. Alrighty, so like when we summarize this work, we are really happy with the start of how the Flux operator is going. We also think this index job abstraction from the batch API is allowing our cluster pods to scale really nicely. And we think there's something to say for the 0MQ bootstrap, although more work is definitely needed to investigate performance. And when I gave my KubeCon talk, I pointed out that this might be the most important point, and I'll say that again here. So if you're familiar with Kubernetes, there's sort of this infamous etcd API bottleneck, and it's that bottleneck that really prevents high throughput. People come up with all of these workarounds for getting around that. And so because with Flux, and we can create a mini cluster that has tasks via sub instances in Flux, we could actually get around this bottleneck. Of course, we'd have to do kind of more testing and figure out how to correctly submit those jobs, but we are very optimistic about this idea. Okay, so what are next steps? So one super exciting piece of this work is that we started kind of officially collaborating with Google Cloud. So right now we've started some experiments to look at how the Flux operator compares with setting up Flux on bare metal, aka compute engine. And we're going to be starting some more experiments with the Kubernetes team very shortly. And those experiments include some of the ones that we alluded to earlier. So all together now, coming full circle, we're going to be looking at Flux as an external orchestrator and also that elasticity thing. And we are really excited about this work in progress. We really want to better understand how to map these HPC workflows to the cloud and do some of these bare metal and networking experiments. So just to kind of quickly show you, here's some places to go if you want to learn more about the projects. Likely you can come to this slide later in the PDF. And I want to close with something really exciting. So we are working on an IEEE special issue on converged computing, a best of both worlds of HPC and cloud. So if you are doing some kind of work that is between the space that might be automation or workflows or containerization or software development or employment, like there's so many cool things in this space. We hope that you look at the special issue and you consider participating. We're looking for not only people to submit papers, but we're also looking for people to review. So if any of this sounds interesting to you, or if you just have questions, please reach out to us and let us know. We would absolutely love to have you. I'll also point out, we're having a little bit of fun. So the final set of papers will have a special edition of Magic the Gathering cards in celebration. So on that note, thank you on behalf of myself and Claudia. We are super excited and very grateful to have spoken today.
So much. And well, just to let you know, Claudia Misale and Vanessa Sochat have been following this session since 2 a.m. Since 2 p.m. here, which is, I believe, 5 a.m. in PST time zone. So yeah, another applause for that. Thank you. So I guess that we can have a connection with them through Zoom. Can you please check that? In the meantime, I think we have time for a couple of questions. Okay, so I'm going to start. So once they get in, they can answer that question. So we have seen different implementations in this talk. Hi, Claudia.
Hi, everyone. Is it work? I guess so. I hear my voice back.
Yes, we can hear you.
Okay.
Do you get yeah? Can you enable the camera?
I think so.
Sorry, I had this request, but now I realize that it's 5 a.m., so probably it's not.
Oh, no, it's not that early. Not anymore. So we are wide awake. I mean, it's earlier for Vanessa. She's in a worse time zone for for this time, but yeah, we are here.
Okay, thank you. So, quick question. So, so how is this implementation suited for production? And how is the funding of the project from the IBM point of view and from Lawrence Livermore point of view?
Okay, so I can answer part of it. I hope Vanessa is able to take part of the question. So for the production level of the tools that we are presenting, for the Flux Operator, I will let Vanessa talk about it, and that's absolutely production grade, but she can take over the question. And for the plugin scheduler that we worked on, I guess, so for that one, we are still doing some adjustments because we want to make that more production grade. And we are also having some collaboration with other institutions and companies to fix all the things that we didn't foresee when we started the implementation, because it started more of a like let's try and see what happens, but then things started to happen, and then bugs arise and all that stuff. But we're working on that. For the on the funding side of the story, so this is a kind of, I mean, it's not super large collaboration, but there are different entities involved. Is IBM Research, is Livermore, is Red Hat too, other universities also from the United States that just joined us. For instance, the University of Tennessee. They just joined us, and we are working on enabling more complicated and larger workloads and workflows through the Flux Operator. But all of that, this is not bound to any kind of contract, let's say. This is all open source, and we want to keep this open, and there's no reason to put any of that under any contract or anything like that. So, which means that whoever is interested in taking a look and maybe work with us or anything, that's all open. And we are very happy to have more people, the more the merrier, and to be more productive and face new problems and try to solve them for this Cloud and HPC Convergence. So Vanessa, are you with us?
Can you hear me?
Okay, yes. Okay, so for I will let you talk for the Flux Operator. That's your creature.
Awesome. So I am not going to go on camera. I am in my pajamas and nobody wants to see that. So first I'll say the Flux Operator is definitely production grade in the sense you can install it on a production cluster today and you can use it. If we kind of had it used in something like a national lab setting, we would want, of course, more sort of security audits and checks. That said, it is a research project in the sense we work on it very quickly and we tend to kind of merge those changes in as soon as all of the tests pass. So it's good to keep abreast of that. I will note for a production setup, so the way we did our experiments was using EFA, Elastic Fiber Adapter Networking on AWS, and that really gave us really great network connectivity, at least for the cloud, that allowed for those times. So all the cloud providers that you tried might have something similar. So for example, right now we're doing tests on Google Cloud and we haven't found the exact equivalent match yet, but that's why this space is so exciting to work in, because we're trying to figure that out so the next person down the line can do that. In terms of funding, so this whole converged computing project is under this entity called an LDRD at the lab, which is a huge I don't know the details really, but it's a huge bucket of money that's able to fund a project. I'm one of the collaborators in LC, so Livermore Computing. I'm actually funded under Flux, which is sort of separate, but they're all sort of connected in one happy family. Did I capture all those questions? I'll also add on, as Claudia mentioned, the Flux Operator is another, it's totally open source on GitHub. You can show up, you can contribute. Absolutely love to have you.